Hello. Continuing with complex numbers, this will be on different way of expressing them, what's called trigonometric form. This different form comes from geometry again, so let's start with the argand plane or complex plane, and let's have a complex number a plus ib somewhere here. So it has real part A and imaginary part B. And this is using Cartesian coordinates. This is setting one-to-one correspondence between points on the plane in place of real numbers according using the recipe of René Descartes. So let us call it that, a plus ib. Instead of Cartesian coordinates, we can coordinatize a plane by different pair of real numbers. So having just this origin fixed and then this direction, we can measure the distance from our point to the origin and call it rho. That was called the absolute value before, but let's call it rho. And then measure this angle, call it phi. And these pair of numbers are called polar coordinates, so we have rho definitely, yeah, let's just bring back the old notation we used. The absolute value rho is a non-negative real number. And then phi is an angle with a fixed line, and as such it's not really a real number, so we can say that it is a real number in between 0 and 2 pi, and 2 pi we have to exclude them. Or we could say that this is an element of real numbers, but if we shift our real number by a copy of 2 pi, an integer copy, we won't feel the difference, and that is the better way of making sense of what is going to be called the argument of that. So this angle is really an infinitude of real numbers. Each of those infinite sequences differ from others by some number of copies of 2 pi. 2 pi is encoding the full circle, and so bring us back to where we were. So shifting arithmetically by 2 pi is not going to change the angle. And then let's do the rewriting. Let's do this trigonometric rewriting from polar coordinates, from knowing rho and phi to just computing the A and the B. So what is A? Well, if rho would be length 1, then that is what we call cosine of phi. But everything is now scaled up by rho, so we have to scale up the cosine projection as well. And the same as B, it is scaled up sine of phi. Again, we're using that just the definition. This side in the triangle with the angle phi and the hypotenuse 1 is called the sine. And finally we can rewrite it into a product of rho and then the sum of cos of phi and I sine of phi. So that is what is called a trigonometric form. Let's see how multiplication works in these coordinates, in the polar coordinates. And for that, we already have a product, so one of the coordinates is just a factor in the presentation of our number. So when we multiply two numbers z and w, their absolute values will have to multiply. We knew that before anyway. So let's just assume, not to drag them from our computation, that the absolute values of our two numbers are both 1. So the numbers are on the unit circle in a distance 1 from the origin. And the first, both are just determined completely by their second coordinates, by their arguments. And we have, say, z here, and w is going to be cosine of some other angle psi plus I sine this angle psi again. So let's compute, using our knowledge of the product, let's compute the answer again for the argument of the product, because the again absolute value of the product is going to be one where we know it before without any computation. Let me write them again. In the product, and here I have cos psi plus I sine psi, and then just remembering what I should do to see the real and the imaginary part of the product. Well, I'm just multiplying real parts first, it's cos phi, cos psi, and I'm multiplying imaginary parts, sine phi, sine psi, but then I'm taking them as minus because they come from, the minus sign comes from I squared, and then the imaginary part of the product will be cos of phi and sine of psi, and with plus sine of phi and cos of psi. One more push. Oh, that's a big push. So we have to remember trigonometry, beloved trigonometry. Does it look familiar? It's supposed to, because this is nothing but cos of the sum of the angles. And in the same time, this is the sine of phi plus psi. So I ended up with something which looks like a trigonometric form again of a complex number. The argument of this number is the angle of inclination of this pointer towards the number is the sum of the angles. So we have this very nice, satisfactory rule of multiplication in polar coordinates. The distances multiply, the arguments add up. That is emphasized by the following compact notation for this beat in a trigonometric form, which is called Euler's notation. Let's just first denote it as e to the I phi. So e is the old natural base for the exponent, and I times phi is this purely imaginary number, and we use it as the exponent. Well, that is a bit cryptic, but at least one one thing is clear, that when we multiply these numbers, so here we have e to the I phi, and then we multiplied it with e to the I psi, the result was e to the I phi plus psi. So this rule becomes very straightforward. This is suggested by the notation we use, because it's kind of natural to multiply in two powers to add up the powers. And that is one formal justification for using this notation. So let me give a more informal one. Let's this notation is actually is not just a notation. This is really a coincidence of two functions. On one side we have a function of real argument phi with complex values. On the other side again we have a function of real argument phi with complex values. Functions are can be defined by Taylor series. So we can look at a sequence of numbers given as appearing as summands in the series. Let me start with this side. Well, imagining this sequence of numbers is easy because everyone remembers the Taylor series for the exponential. It's let me write it first in a compact form. It's just the sum of all powers of the argument, and each of those powers is divided by the factorial, and then it's the sum of all, not negative. So spelled out it will be 0 power, which is just 1, then the argument, which is I phi phi, the argument of the exponential function. Then the argument squared over 2 factorial, then the argument cubed over 3 factorial, the 4th power of 4 factorial, and so on. So let's see what happens with these powers. Well, nothing much I can do with the first two, but the third one I can rewrite into something better looking, because what I have here is I squared times phi squared. I squared is -1, so we'll just write it as such. What happens next? So then I have the cube of I, and maybe if it is not too much, maybe I should just look at only the only the even powers. So then I will just save this till later. I will cross it out. I will look at only the even powers first. I'll have 0th power, then I have a square, then I have the 4th power. So what is the 4th power? The 4th power is the 4th power of I times 4th power of phi. And I to the 4 is 1, because I squared is -1, so the square of -1 will be positive. And then you can see what is going to happen. The next one will be negative again, because it will be the 6th power of I in front of phi to the 6, and that is minus again. And the signs will alternate, and the members of this series you could see what they are. So let me collect now with I in front all the odd powers. So I will factor I from them, because they will all have a multiple of I in them. And the remaining thing will be first phi, then I have I cubed times phi cubed over 3 factorial. Well, I cubed is I times I squared, which is -1, so I should have left negative. I already took outside, so then after that it will be just -1, it will be just I squared. And that is the coefficient for phi cubed over 3 factorial. Then I have plus again, which will be coming from the 5th power. And again, you can see what happens. In the compact notation, you'll have the first sum encoded like that. So you only have even powers. Let me write them as 2k. And then below is 2k factorial, just the same factorial as the power. And the sign depends in this flickering pattern, in this alternating pattern, on the power. So for the 0 it is positive, for 2 is negative, and so on. How can we encode it in a formalic way? Well, this is 2k with k being 1, and we have negative. Just put k here, and you can see that this really accounts for the correct assembly of signs. So k is a running index from 0 to infinity. And the second, coming with coefficient I, is a similar one. So now we have all odd powers. 2k plus 1, power of phi is a generic term. The denominator is 2k plus 1 factorial. And again, the sign changes. It is positive for the very first member, negative then, and then alternating. So the first member is when k is equal to 0. When k is equal to 1, it's negative, and so on. It will be changing as it should. So the last bit is to remember what is this is a Taylor series of. And from your calculus knowledge, you should see that this is Taylor series of the cos of phi. And the same way, this is a Taylor series for the sine of phi. So we proved that this is not just a formal definition, it's something with a substance. It is a coincidence of Taylor series, one for the exponential function and the other two are for the sine and cos functions put together using complex numbers. And yeah, I think it's a great way for actually remembering the Taylor series of cosine sine. Complex numbers help also remembering the trigonometric formulas for cos over sum and sine over sum. It's easier to remember how to multiply complex numbers than all this complex trigonometry. So that will be it for this. See you later.